video, we are going to look at the solubility product, or KSP. But before we can start that, we first need to recall what these solubility rules are, because these are going to be very useful for us to use to figure out whether we have a solubility equilibrium or not. So to review, our solubility rules are here on the slide. So our first one is that all nitrates are soluble. Okay. Our second one, all ammonium or alkali metal compounds are also soluble. Our third one, all carbonates, phosphates, and hydroxides are insoluble unless they are with an alkali metal or with an ammonium ion. Fourth, all chlorides, bromides, and iodides are soluble unless they are paired with silver, lead, or mercury. And finally, all sulfates are soluble except when they are with calcium, strontium, barium, radium, or lead ions. So what does this have to do with solubility? Well, if you have a compound that is highly soluble, then what that means is when you take that compound and dissolve it in water, it will completely dissociate into its ions and no equilibrium is formed. But when you have one of these compounds that has low solubility, an equilibrium is formed. And so we can write an equilibrium expression for it, we can figure out an equilibrium constant for it, and we can do various calculations. Okay, so the first thing we're going to do is take a look at some examples. And we are going to identify first whether these compounds have high or low solubility, and then write out the corresponding dissociation equation for each. Okay, so let's begin. First with calcium hydroxide. If we take a look back at our solubility rules, that compound has low solubility. So this means that it will establish an equilibrium when dissolved. So we're going to write out a dissociation equation with a double arrow because this is an equilibrium situation. So it is going to slightly dissociate into calcium ions and two hydroxide ions. For our second compound here, it has high solubility. So for this one, sodium nitrate, it will completely dissociate into sodium ions and nitrate ions. Okay, so we're using a full arrow here because it completely dissociates into its ions. Silver chloride is low solubility. So again, it will establish an equilibrium and slightly dissociate into silver ions and chloride ions. Okay, if we take our last equilibrium expression that we created, our silver chloride solid is in equilibrium with silver ions and chloride ions. And so we can write out a equilibrium constant expression to go along with this equilibrium equation. Now, because it's based on the solubility of only low soluble compounds, we have a special name for this constant. It's called the KSP, or the solubility product constant. So to write out a KSP, it's the same as writing out any K expression. So we're going to take the concentration of our products. So our silver ions, we're including that because it is aqueous. And our chloride ions, because we're including that again because that is aqueous. And then typically what we would do for a K value is we would divide that by our reactants. But I need you to take note here that our reactants is a solid, so that means that we do not include that in a K expression. It's actually a constant value, so it's taken care of in the constant value alone. So that means that our KSP expression is just our silver ion concentration times our chloride ion concentration. So now what we're going to do is we're going to take a look at a couple of examples and see some problems and how to solve them using KSPs. Our first question here says a chemist finds the solubility of silver carbonate, or Ag2CO3, is 1.3 times 10 to the negative 4 moles per liter at 25 degrees Celsius. And we want to calculate the KSP for this compound. So the first thing we want to do, and the first thing we always want to do with questions like this, is write out our balanced chemical equation. So it's important to recognize that silver carbonate is a slightly soluble compound. So it is going to establish an equilibrium with its ions. So we've got silver ions and we've got carbonate ions. Now the next thing we're going to do, because this is an equilibrium, is we're going to set up an ice table. So remember, I is for initial concentration, C is for change in concentration, and E is the equilibrium concentrations. Now, because silver carbonate is a solid, it doesn't matter what those values are because it's a solid. So it's not even included in our K value. We're just going to put lines there. For our ions, initially when we take silver carbonate and we put that in water, the ion concentration is 0. But as it slightly dissolves, that is going to change until it reaches its equilibrium. Okay, and the change is going to happen the same way it happens in any equilibrium system. It is based on stoichiometric ratios. So the silver is going to go up by 2x, and the carbonate is going to go up by x. Now, it's really important to note here that x is the molar solubility of the compound, because only what can dissolve is going to be found in solution or in this ion form. Okay, so X is defined as your molar solubility at this point. And then to get our equilibrium expressions, we're just adding up our I and our C columns. So for silver, it's going to be 2x, and for carbonate, it's going to be x. Our next step then is to come up with a KSP expression. So let's do that. We're going to do KSP is equal to our silver ions, and we need to square that because of the 2 here, times our carbonate ions. So we're solving for KSP, and let's plug in our equilibrium expressions from our ice table. So for silver, we've got 2x, and that's all squared, times x. Or KSP is equal to, now remember, the 2x is all squared, so that's going to become a 4x squared times x is going to become 4x cubed. Now remember, x is our molar solubility, so we need to take our molar solubility given to us in this question and substitute that in. So we're going to have 4 times 1.3 times 10 to the negative 4, all cubed, which is going to give us a KSP value. And we need to consider significant digits here. So that's going to be 8.8 times 10 to the negative 12. On to our second example. So for this one, we're given a KSP for barium carbonate, which is 8.1 times 10 to the negative 9, and we want to calculate the solubility of barium carbonate in moles per liter. Again, really your first step in any of these kinds of questions is to write out a balanced chemical equation. So we need to recognize barium carbonate is slightly soluble. So it is going to form an equilibrium with its ions. We've got barium 2 plus ions, and we've got carbonate ions. Now, because it's an equilibrium, in order to solve for the solubility, we need to make use of an ice table again. Remember, we don't need to include any values for the solid here because it doesn't end up being part of our KSP expressions. We're just going to put lines there. And again, barium and carbonate ions are initially 0. In order to change to reach equilibrium, both of these ions are going to go up by X, and so their equilibrium concentrations are going to be X. And you have to remember and keep in mind that that X represents the molar solubility. It's what we're trying to solve for in this question. So next we're going to set up our KSP expression. So that's going to be our barium ions times our carbonate ions. So those in molar concentration. Now we're given a KSP in this question, so we're going to plug that in, 8.1 times 10 to the negative 9. And then we're going to plug in our equilibrium expressions for the barium and carbonate ions. So that's X times X. Okay, let's take this one more step. So 8.1 times 10 to the negative 9 is equal to X squared. And we're going to solve for X here. So we're just taking the square root of both sides. And that is going to give us a value of 9.0 times 10 to the negative 5. So what this means is that the molar solubility is equal to 9.0 times 10 to the negative 5 moles per liter. So that gives you an example of both kinds of problems. One where you're given the molar solubility and you're asked to find a KSP, and the other type of problem where you're given a KSP and asked to find the molar solubility. Hopefully that helps. See you in the next video.